Okay. So what we're gonna do is section 2.6 quadratic surfaces. We're gonna do all of 2.6 and half of 2.7, and then on Thursday we'll finish 2.7 and do all of 3.1. Probably not gonna take us till 7 o'clock or 7:30. We'll probably get done a little bit early on both days, but we'll see how it goes. So, all right. 2.6 quadratic surfaces. We're talking about items where we're in three-dimensional space. So you can see here on the left-hand side that we have the graph of the equation z equal to x cubed is a cylinder or a cylindrical surface with the rulings parallel to the y-axis. And then we have a nice definition. A set of lines parallel to a given line passing through a given curve is known as a cylindrical surface or cylinder. The parallel lines are called rulings. Okay, so you're going to want to go ahead and write that stuff down if you're a physical note taker. And because I can't see any of you, a few of you at least are going to have to give me a thumbs up so I know I can move to the next slide. Just a second. Oops. Right. Okay. All right. Brianna, you can just maybe take a quick screenshot of this slide, or you can always get it off the PDF that I upload. All right, so try to do something a little bit different because a lot of the solutions for this section or for these sections had graphs. Sketch the graphs of the following cylindrical surfaces. So instead of me ridiculously butchering that, I just stole them. So I'll remove the sticky notes when we're ready for it. So the first one says x squared plus z squared equals 25. So what everyone should notice is that we only have x and y that we're dealing, or sorry, x and z that we're dealing with. And you should also be screaming at you that it's going to be some kind of circle, right? Because it's following that circular pattern. So here what you want to realize is that the variable y can take on any value. Without limit. And so because of that, so therefore the lines ruling this surface will be parallel to the y-axis. Okay. So the only other thing that you need to pull out here is that the intersection of this surface with the xz plane forms a circle centered at the origin and radius 5. Okay, which you guys probably could have gotten there. Intersection with x z plane at origin and radius 5. So now we're going to see what that looks like. I'm gonna get rid of that and probably pull it down a little bit so you can see it a little bit better. Okay. All right. In the second part, it says z equals 2x squared minus y. So in this case, the equation contains all three variables, x, y, and z. So none of the variables can be arbitrary, just like we used with the y last time. So the easiest way to visualize this surface is to use a computer graphing tool. I'm going to assume you guys aren't going to have to worry about this type of thing on your exams, except to just kind of know what it is, to recognize it, because you guys can't really use those tools anyway. All right, and then the last one is y equals sine x. So in this equation, we can see that it's just got y and x, so that should take us back to our algebra days, which means that variable z can take on any value without limit. Therefore, the lines composing this surface are parallel to parallel to the z-axis. So then we're looking at a surface with an intersection between the xy plane and the sine x curve. So that's going to look like this. So here, for C, Z is arbitrary, meaning intersection with XY plane. Uh, so A, C, B. All right. So I will be putting this PDF up in case you guys need more time with that. I would not, I mean, you can try to draw these, but you can also maybe print them out and maybe glue them into your notes. I don't know. I use my tablet for my notes. So. All right, so we have a nice definition here. The traces of the surface area are the cross sections created when the surface intersects a plane parallel to one of the coordinate planes. So you can see in A, this is one view of the graph of the equation z equals sine x. And then B, to find the trace of the graph in the xz plane, set y equal to 0. The trace is simply a two-dimensional sine wave. Okay, so here you can notice that we have x and z, not x and y. because y was set to 0. Okay. Oh, oh, technology, how I thoroughly enjoy that it doesn't work. All right, we're going to do another example. But before we do, we're going to talk about quadratic surfaces. So what we've learned about surfaces in 3 dimensions described by first order equations, these are planes. Some other common types of surfaces can be described by second order equations. We can view these surfaces as 3-dimensional extensions of the conic sections we discussed earlier. The ellipse, the parabola, and the hyperbola, we can call these graphs quadratic surfaces. So that's what we're going to kind of move into next. Let me kind of move this to the side a little bit so you can see. So, we're dealing with this definition, right, of quadratic surfaces are the graphs of equations that can be expressed in the following form. So you're always going to have ax squared plus by squared plus cz squared, and then it's just going to keep going. You can have zeros for a bunch of those. You can have some of them included and some of them not. So it's quite the lengthy formula to try and sit there and memorize, but has a pattern, so you guys should be good to go. Sketching an ellipsoid is our next example, but before we do that, let's look at this other statement. When a quadratic surface intersects a coordinate plane, the trace is a conic section. An ellipsoid is a surface described by an equation in the form x squared over a squared plus y squared over b squared plus z squared over c squared equal to 1. Set x equal to 0 to see the trace of the ellipsoid in the yz plane. To see the traces in the xy and xz planes, set z equal to 0 and y equal to 0, respectively. Notice that if a and b are equal, the trace in the xy plane is a circle. Similarly, if a and c are equal, the trace in the xz plane is a circle. And if b and c are equal, then the trace in the YZ plane is a circle. A sphere then is an ellipsoid where A, B, and C are all equal. Okay. So going to show you these. So I would recommend writing down the first one is we're setting Z equal to 0. I'm gonna get rid of that so you can see it. And then we have Y equal to 0. And X equal to 0. Okay, looks very similar, obviously, but you can see a little bit of differences. So then once you have these are your traces, okay? These 3 items, that kind of looks bad, but so these are your traces, okay? And then once we have our traces, We then would have our framework. So this is our framework. Okay. And then the final, like, overarching answer, I guess, if you wanted to say, would be this ellipsoid. Centered at the origin. Okay. So obviously you would want to give all of that in your answer. You can't really get to the framework until you do the other three. So you have to do your traces. And you can see here, this part would be A, this part would be B, and then this outside part would be C. So those are your three traces. Okay. Everybody seeing how that one's coming together? Thought it was a pretty nice example. And then again, you can see that it's only using those first three in that definition. Oh, of course. Okay. Just gonna scoot it down a little bit so you can get the words, and then I can move it back up for the image. So the trace of an ellipsoid is an ellipse in each of the coordinate planes. However, this does not have to be the case for all quadratic surfaces. Many quadratic surfaces have traces that are different kinds of conic sections, and this is usually indicated by the name of the surface. For example, if a surface can be described as an equation of the form, and you have that form, then we call that surface an elliptic paraboloid. The trace in the xy plane is an ellipse, but the traces in the xz plane and yz plane are parabolas. Other elliptic paraboloids can have other orientations simply by interchanging the variables to give us different variable in the linear term of equations. Okay, and then you can see uh, your picture there. Whenever I do the power or the PDF, it gets rid of the slide numbers, so you'll be fine. Okay. All right, so number 6, or uh slide 6, yes, third example. It says identifying traces of quadratic surfaces. Describe the traces of the elliptic paraboloid. I'm probably going to say that differently every single time. So we have x squared plus y squared over 2 squared equals 5, z over 5. So to find the trace in the xy plane, we want to set z equal to 0. So that means we're going to take x squared plus y squared over 2 squared equal to 0. Let's define the xy plane. Okay, so the trace in the plane z equals 0 is simply one point, the origin. Since a single point does not tell us what the shape is, we can move up the z-axis to an arbitrary plane to find the shape of the other traces of the figure. So that's why we're going to look at the trace in the plane z equals 5. Okay. So the trace in the plane z equals 5 is the graph of the equation. So what we're doing here essentially is we're having we're gonna have x squared plus y squared over 2 squared. 2 squared equal to 1. because we're setting z equal to 5, which would be 5 over 5, which is 1. And this gives us an ellipse. Okay. In the xz plane, the equation would become z equals 5x squared. Which you guys should remember is a parabola. The trace is a parabola in this plane and in any plane with the equation y equals b. Right? In planes parallel to the yz plane, the traces are also parabolas. So this is also going to be a parabola. All right, so let me show you what they look like. Y equal, nope, z. Z equals 5. I think that's the only thing we needed for that. Let's x, z plane, and y z plane. All right, so now you guys kind of have an idea of what each piece is. Right? Okay, so once you have all of that, you then have to bring it together. That is what you would get. Okay. So you can see this would be your top spot. Right, and then this is the wider portion. And this in here. Okay. Right. Right. So yeah, A, B, C, D, we got them all. All right. We have another problem. So it says, energy hitting the surface of a parabolic reflector is concentrated at the focal point of the reflector. If the surface of the parabolic reflector is described as the following equation, where is the focal point of the reflector? Okay, so we are talking about an application-based problem, right? So since z is the first power variable, the axis of the reflector corresponds to the z-axis. So part of that is going to be in the z-axis. Don't know why people are choosing to bounce out, but whatever. So the coefficients of x squared and y squared are equal. So the cross section of the paraboloid perpendicular to the x-axis is a circle. Sorry, z-axis. So x squared and y squared being equal, perpendicular to the z-axis will be a circle. All right. So the cross section is going to be a circle. We can consider a trace in the XZ plane or the YZ plane. The result is going to be the same. So let's set Y equal to 0. The trace is a parabola opening up along the x-axis, and we would have x squared equal to 100 times z over 4, which would just give us oh, we're trying to find the point. So so then if we rewrite that, we get x squared equal 4pz, which is going to give us 25 4pz. Sorry, there's an extra equal sign in there. I skipped it. It just basically needs to move. Okay. So, or, oh wow, my computer finally started to work. Okay. So P is going to be equal to 6.25 meters. So then that gives us the focal point at 0, 0, 6.25. Tiffany, only because I can now see the computer. Do you have a question you want to say out loud or in the chat, or?
Just a quick question. We know it's going to be on the x-axis because that's the only variable that's not squared. Is that how we determine that?
So the z-axis, but yeah, because that's your first order. Yep.
Okay.
Yep.
Thank you.
You're welcome. All right. Okay, so these next couple of slides, I'm pretty sure, are just ones that you'll probably want to get either from the textbook or the PowerPoint. It's just a lot to write down, but I do think it's important information for you guys. So there are 17 standard quadratic surfaces that can be derived from this general equation. That's a lot. So I pulled them out for you. They cover this slide and the next one. I would not try to squint and see all that. Just wait until it gets posted up. But what we have are the ellipsoid, which we've already gone through a couple of those examples. That's the x squared over a squared plus y squared over b squared plus z squared over c squared equal to 1. So that is that ellipsoid shape. Then you have a hyperboloid on one sheet, a hyperboloid on 2 sheets, and you don't have to worry about writing that down right now. It will be on the PowerPoint or PDF. Then you have an elliptic cone, an elliptic paraboloid, which we've discussed as well, and then a hyperbolic paraboloid. Oh God, such a horrible name. All right, so those I would strongly recommend flashcards, something, however you want to do it. That's how I would work those and make sure that you know what you're doing on that. Okay, so this is our last example in 2.6. It says identifying equations of quadratic surfaces. Identify the surfaces represented by the given equations. So the first one we have, so for A, okay, we're given 16 x squared plus 9 y squared plus 16 z squared equals 144. All right, so x, y, and z are all squared, and they're also all positive. So that's actually going to tell us that this is an ellipsoid. And this is using those charts that I just showed you. However, if we want to put it into standard form, we have to do a little bit of work. So notice from that, I'll show you here. This form here, we need to have it equal to 1. So that's what we have to do there. Right? And we'll probably go back to that other slide. So we're just going to divide everything by 144. And so we'll get 16 over 144 x squared plus 9 over 144 y squared plus 16 over 144 z squared equal to 1. Well, I guess if I want to stay consistent, 144 over 144. Then we'll go through and simplify. So we'll have x squared over 9 plus y squared over 16 plus z squared, z squared over 9 equal to 1. Okay, so your base answer is that, but then additionally standard form. Which would be a good way to, verify to yourself that you did that correctly. You identified it correctly. All right, so part B. It was 9x squared minus 18x plus 4y squared plus 16y minus 36z plus 25. And that was all equal to 0. And I guess before I show you that answer, this is also centered at the origin. Okay. All right. Okay. So what you'll notice is that we have x squared and x, y squared and y, but we only have one term for z, and it's to the first power. So that's the first thing you should notice. So that means this could be a few different things. It's either going to be an elliptic paraboloid or a hyperbolic paraboloid. We also notice that there are x terms and y terms that are not squared. So this is a quadratic surface that is not centered at the origin. Okay, so not because then we're going to have to do some extra work. I don't understand why i's are so hard to write on here. So we need to complete the square to put this equation in standard form. Okay. So this is going to be long. So we have 9x squared. I'm not going to rewrite it. I'm just going to go straight from where we're at. 9x squared minus 18x plus 4y squared plus 16y equal to plus 25 equal to 36z. All right. Now we're going to pull out our 9 and we'll have x squared minus 2x plus pull out our 4y squared plus 4y plus 25 equal to 36z. Okay. All right. Okay, so the next step, in case anyone is a little rusty on the algebra, we are adding and also subtracting in the same set so that we have that balance, but we don't have to take the extra steps. So that's going to give us 9x minus 1 squared plus 4y plus 2 squared plus 25. I forgot the minuses. Sorry, guys. Hold on. Plus 2 squared minus 16 plus 25 equals 36z. And then we'll have our 9x minus 1 squared plus 4y plus 2 squared. And then our minus 9, minus 16, and 25 all cancel. So we're equal to 36z. And then we're going to divide everything by 36. So we have x minus 1 squared over 4 plus y minus 2 plus 2 over 9 equals z. Okay, so that makes this an elliptic para centered at 1, 2, 0. I'm just gonna give you guys what the book has. I'm just saying mine. There's a sign somewhere. All right. So that is section 2.6. I want to save the PDF real quick. because I don't know if we use that. Okay. And then we're going to move right into 2.7. We are only going to do the first 5 slides because then we can pick up on it on Thursday. All right. So pretty big definitions here. So 2.7 is cylindrical and spherical coordinates. There we go. Definition: in the cylindrical coordinate system, a point in space is represented by the ordered triple r theta z, where r theta is the polar coordinates of the point's projection in the xy plane. Z is the usual z coordinate in the Cartesian coordinate system. So there are conversions here. You will have to work with them on your homework. I'm sure they'll be on your exam. So I would definitely know these at least. I know I'm either going to make my own cheat sheet or, formula sheet, or I guess a better terminology there. Or I'm gonna find one. So I'm not sure if these are gonna be on there. So I would know them to an extent if you don't already. So x is going to be equal to r cosine theta, y is going to be equal to r sine theta, and z, of course, is equal to z. And then we have r squared is going to be equal to x squared plus y squared. Tangent theta is going to be y over x, and z is equal to z. Again, you're going to have all of this online. So I pulled these for you. I thought they were pretty good at showing you all the pieces. So it shows you from, kind of this idea here on the first page to translating it into the triangle that we're used to working with. The Pythagorean theorem provides the equation of r squared equal to x squared plus y squared. Right triangle relationships tell us that x is equal to r cosine theta, y is equal to r sine theta, and tangent theta is equal to y over z. So there is all of that kind of recapped for you. Figures 2.91 and 2.92, they are showing you the rectangular coordinates and what they are versus the cylindrical coordinates and what they are. Okay, so I just thought that it was interesting for you guys to have that available to you. Okay. All right, so let's do an example, converting from rectangular to cylindrical coordinates. So we want to convert the rectangular coordinates 1, -3, 5 to cylindrical coordinates. So the first thing we want to look at is we have r squared equal to x squared plus y squared. So if we fill that in, we would have r squared equal to 1 squared plus -3 quantity squared. Take the square root of both sides. So that will give us r equal to plus or minus the square root of 10. Okay, we choose the positive root, which makes sense because we're talking about lengths. Now we can apply the formula to find theta. In this case, y is negative and x is positive, which means we must select theta to be between. So given that x is positive and y is negative, then theta lies between 3 pi over 2 and 2 pi. So then we can actually use tangent theta, and we know that we have y over x is that's going to be -3/1, which is just -3. But that's the tangent of theta equal to -3. So then you would have to theta is equal to the arctangent of -3 plus 2 pi. So that gives you theta equal to roughly 5.03 radians. Okay. In this case, the z coordinate is the same for both, so z is just going to stay equal to 5. So if you want to write it in point form, we would have the square root of 10, 5.035. Okay. So that should be pretty nice for you guys to do some of those problems. All right. All right, cool. I can see you guys, so hopefully you are good to go there. One last big example and then just some notes and we'll be done. So this slide says identifying surfaces in the cylindrical coordinate system. Describe the surfaces with the given equations. So we have theta equal to pi/4. Then theta is held constant while r and z are allowed to vary. So the result here is going to be a half plane. Okay. So that's your half plane there. Theta equal to pi/4. All right, so pi/4, as long as theta is equal to pi/4, r and z could be anything. So it's going to be that parallel plane having that orientation there. All right, part B says r squared plus z squared equals 9. So if we substitute r squared equal to x squared plus y squared into the equation, we would have r squared plus z squared equal to 9. If we sub that in, then it's going to look like this. So this is for B. Oops. You can stay there. This is for B. So if we know that r squared is equal to x squared plus y squared, then we would have x squared plus y squared plus z squared equals 9. This equation describes a sphere centered at the origin with a radius of 3. So this is a sphere centered at the origin with a radius of 3. Okay. And that's what that one looks like. Okay. And the last one says z equal to r. To describe the surface defined by the equation, it is useful to examine the traces parallel to the xy plane. For example, the trace in plane z equals 1 is a circle with radius 1. The trace in the plane z equals 3 is a circle with r equals 3, and so on. So each trace is a circle. As the value of z increases, the radius of the circle also increases. So that's what this looks like. Okay. So you guys can kind of see why I chose to leave the solutions visual. So each trace is a circle. As z increases, the radius increases. Okay. Okay. We're just gonna do one last bigger note section, and then that's it. So our definition here is in the spherical coordinate system, a point P in space is represented by the ordered pair, or the ordering rho, theta, and phi. Couldn't figure out which one was first, but that's rho. Okay, and again, it shows you a nice little diagram. It has your converting charts. We actually might pick up here on Thursday, because I imagine the following examples lead with that. Okay, so let me go ahead and stop the sharing.